In the last video, we started to construct a space-time diagram from my frame of reference, and I'm just drifting through space, and I'm assuming that I'm in an inertial frame of reference, which means I'm moving at a constant velocity relative to all other frames of reference. And we set up a situation where I emitted a photon right at time 0. So after 1 second, it would have moved 3 times 10 to the 8th meters. After 2 seconds, it would have moved 6 times 10 to the 8th meters. And then we added a little bit of flavor to our little scenario, where right at time 0, a friend passes me up in her spaceship, and she's traveling relative to me in the positive x direction at half the speed of light. And so we plotted her path. Right at time 0, her spaceship is right there. I could draw the spaceship. It's at the origin. Then after 1 second, she would have traveled 1.5 times 10 to the 8th meters. After 2 seconds, she would have traveled 3 times 10 to the 8th meters. So this blue line in the last video was her path. But now I want to make it even more interesting. Let's assume that we have actually a whole train of spaceships all traveling in the positive x direction at the same velocity as her spaceship. So this is her spaceship right over here. At time equals 0, she is exactly where I am. But let's say that 3 times 10 to the 8th meters in front of her, there's another spaceship traveling at exactly 1.5 times 10 to the 8th meters per second. So they're traveling at the same relative velocity to me. But if you think about it from each of their point of view, they would seem to be stationary because the distance between them in this x direction is going to stay the same. So this person at time 0 is going to be 3 times 10 to the 8th meters in the positive x direction from me. Now, if I were to wait 2 seconds, they are going to be, so if I were to wait 2 seconds, they are going to be 6 times 10 to the 8th meters away from me because they're going half the speed of light. And so I could draw their path, and I'm going to do it in a slightly more muted, thinner color so that what I'm essentially going to be doing here is I'm setting up grid lines for my friend's alternate frame of reference. I'm going to put that on top of my frame of reference. And to be clear, I'm not assuming special relativity. I'm assuming a Newtonian world, classical mechanics, just to get familiar with these ideas and to see where the Newtonian world is going to break down. But let's say that's not the only ship. Let's say there was another ship that at time equals 0 is 6 times 10 to the 8th meters away from me in the positive x direction. Well, where are they going to be? Where are they going to be after 2 seconds? Well, after 1 second, they're going to be 1.5 times 10 to the 8th meters further. Then after 2 seconds, they're going to be 3 times 10 to the 8th meters further. And then after 3 seconds, so they're going to be 1.5 times 10 to the 8th meters further than that. So their path is going to look like, so let me draw this. So I'm really just doing these to show what stationary objects in my friend's frame of reference, how they actually look to me. And these should be parallel lines. So that's a pretty good attempt. And so let me actually just set up that alternate frame of reference. So this is going to be not only my x-axis, I'm also going to call this my x-prime axis. And I'll do in a second of thinking about how we can read this. So I can color this in with the blue color. Actually, let me do it in that light blue color that we're going to be using for my friend's frame of reference. So this is also going to be our x-prime axis overlaid. And this one, let me call this the t prime axis. So my friend's frame of reference, I'm going to call that the prime frame of reference. Or if I called my frame of reference the s frame of reference, I can call my friend's frame of reference the s prime frame of reference. And so let me draw horizontal lines to show the passage of each second. So that's 1 second, 2 seconds, 3 seconds, so on and so forth. So let's make sure we're comfortable with reading what's going on here. So a point, let's say this point on our diagram, let me see, this point on our diagram, from my frame of reference, in the S frame of reference, this is the point, time is, or space, or my distance from the origin in the positive x direction is going to be, I just drop a I just go parallel to my vertical axis. So I'm just going to do that. And I get 4.5 times 10 to the 8th meters. So 4.5 times 10 to the 8th meters. And what is our, so I can write the units there if I want. And our time is at 1 second. 1 second. So this is our coordinates from, this is the coordinates from my frame of reference, from the S frame of reference, I guess S for Sal. And so what would be the frame, what would be those same coordinates from my friend's frame of reference? Let's say her name is Sally, or S prime. Well, from her frame of reference, our time is still 1 second. We see the horizontal line there, and we're just going parallel to our horizontal axis, or our x-axis. So the time is still 1 second, but the distance that the x coordinate is 3 times 10 to the 8th meters. 3 times 10 to the 8th meters. And I really want you to sit and think about this, and even take out a ruler and draw this on your own paper and feel good about this. Now, why does this make sense? Well, you could view this point as where that second spaceship was after a second. And from Sally's point of view, from the S prime frame of reference, at time equals 0, that ship was 3 times 10 to the 8th meters in front of her. And after a second, that spaceship is still 3 times 10 to the 8th meters in front of her. After 2 seconds, it's still 3 times 10 to the 8th meters in front of her. And so from her point of view and her frame of reference, it is stationary. So the way to read this for any point, if you want my frame of reference, the time is easy. You just go horizontally to either one. So on her axis, we've essentially just taken the coordinate axis and sheared it and skewed it. This is still 1 second. This is 2 seconds. This is 3 seconds. But it turned all of these kind of a grid of squares, if I were to draw a grid for my coordinates, into a bunch of parallelograms, which we see right over here. And so for any given point remember, we're thinking of Newtonian space and time. To read it, we go horizontally for time in either case. But for me, you would go straight down because my time axis is vertical. You go straight down and you read where it intersects the x-axis to figure out what our position. But for her frame of reference, we move parallel to her t-axis, or her t-prime axis, I should say, to get what her what her x-prime coordinates are going to be. So this is x prime, t prime, this is x, and this is t. Now what's clear at any given point, t is going to be equal to t prime. Or we could say t prime is equal to t, either way. But what's the relationship between x prime and x? Well, let's think about that for a second. So when x is 4.5 times 10 to the 8th meters, x prime is 3 times 10 to the 8th meters. And so it looks like x prime is going to be equal to x minus, well, what's it going to be minus? It's going to be minus 1.5 times 10 to the 8th meters. But that difference is going to grow as time goes on. Meters per second times the amount of time that has passed by. And you should see that, because after 1 second, the difference is 1.5 times 10 to the 8th meters. After 2 seconds, so let's look at this point right over here. In my frame of reference, that person is sitting at 6 times 10 to the 8th meters in the positive x direction. But in Sally's frame of reference, in the S prime frame of reference, they're still at 3 times 10 to the 8th meters in the positive x direction. So we would multiply 2 seconds times 1.5 times 10 to the 8th. So we have 3 times 10 to the 8th meters. So we take 6 times 10 to the 8th, which would be that. We subtract out 3 times 10 to the 8th, and we get the coordinates in S prime. So this might get a little bit confusing, and the key here is really try to draw this yourself and really try to plot points and think about how they are different coordinates in the different frames of reference, or different time-space coordinates in the different frames of reference.